Welcome to another GC Basic tutorial. It's part 8 of a series of videos for the PIC18xxQ20. Let's get the preamble done. Like the video, let the video run to the end, subscribe to the channel. Need to pay for this open source software. I'm hoping with some revenue from YouTube this year, I can get over the begging emails that have to go out every year. Let's get into the video. So we're going to use serial or the UART of the microcontroller. We're going to send some values out to the terminal, a serial terminal on our computer. Very useful to show you what's going on inside the microcontroller, and I use it extensively for debugging. It is the most obvious thing to do for debugging. Do not struggle any other way. So PIC18xxQ20 comes with a serial UART, and we're going to configure that UART and use the serial commands. Very simple. Right, the hardware, I've got a prototype board, some power, programmer. I'm using a PIC18 still. In the previous video, I showed you how to change it to a PIC18. Very simple. A bit slower to use, but never mind. I've added a serial port, and I've got the same LEDs, potentiometer, and switch. And the port I have selected for the serial is B7. This is very important that we know this because we're going to have to tell the microcontroller where to connect the peripheral called UART to. So remember, port B.7. If we look at Deskcam, here's Deskcam, Deskcam. If we zoom out, here is my UART. Here is my little serial connector. We're going to see that in a moment in a bit more detail. These cost about $2. I'm just going to put that back into my USB port. There we go. Which way does it go? Goes to that way. And I've connected up the 0 volt to the 0 rail here. So that's where it happens to be on mine. And port B.7 here, which then connects it into the back end of the chip over here. The rest of it is the same. So all I've done is connected up a bit of hardware, and it's called USB TTL. Okay, and it's a serial converter, and they're very, very useful. I'll talk about that again, a bit more detail. So the serial, the output, is going to be using the internal USART of the PIC microcontroller through this USB TTL USB serial converter. They look like this. This one, I think this is not the one I'm using, but it doesn't matter. They're all very, very similar. And I'm connected up. I need to connect up the ground, and I've connected my transmit line, which I'll show you, of B.7 to the receive line on there. Or is it the TX line? There we go, the transmit line. But it's very obvious. If you get it wrong, it just doesn't work. To connect, let's just make sure we go back 2 slides. The USART capability, which is in this microcontroller. So let me just bring a pen up. The USART capability in this particular microcontroller, and most of the new ones, you need to set the peripheral, that device up. You need to connect it using a particular set of controls. Those controls are all on the data sheet, but we're quite lucky with GC Basic because we've written our own tool to make it very easy. And that's called the peripheral pin select. So what it gives you is a configuration to join these capabilities of the microcontroller to a very wide range of the pins available, the I/O pins. It really, you can tailor it. I've chosen B.7. You might choose B.3. I don't know what you're going to choose, but you can choose many different inputs and outputs. And PPS allows you to move that capability of the USART to that particular input and output. So to make it work with serial, we need to set the TX using PPS. We have no option but to use that, and we'll do that in a moment. So what we're going to do, we're going to initialize the chip. I'll bring up my pen. We're going to initialize the chip. We're going to set up the serial using, guess what? PPS. We're going to do a do forever loop, and we're going to read the ADC, and we're going to send some values out to the serial. If it's changed, change the direction, and we're going to do some clever stuff. And we're just going to loop round. Now, we're going to look at some code. We're going to look at an example of the end state code, and then we'll rebuild that back into an empty shell. Okay, so I'll explain. Here is the IDE. Control B. There are two files, 100 and 101. 100 has no capabilities. It is exactly the same as the previous 90. What we're going to do is add it in. And I've given you 101 as a complete reference. It's a complete reference, and it's good to have these two because the reference one is 100. The 101 you can sort of hack around and play with it and not break it, and then you can keep putting 100 back on 101. So 100 is your reference. So if I take 100 and I compile it by pressing function key F5, it will compile it up, which is great. Okay, so I'm just going to stop that by hitting the dustbin. Okay, because it's one thing we need to do is start up a terminal application. Well, we can do that in the IDE by pressing function key F9, and it will open up a particular interface, and it's this interface. I'm going to zoom in so you can see it. And this interface is, you might not like, there are better apps out there, no doubt, but I use this one because it works. And essentially what I'm going to do is I'm going to just rescan, and where that little TTL USB connector is COM5, and we are going to be using 9.600 BPS, bits per second. I don't really care what you use, but we're going to use that, and I'm going to connect to that terminal. So in this window here, we will see communications. If I go back into this program, back into the main screen so we can see it, Control B to get rid of the side window, function key F5, it will program it up. I'm now going to toggle out to the terminal, zoom in on that. In the background, you'll see it sort of program things, great, wonderful. But we just want to show you what it can do. So it says GC Basic 2024, a 16 Q20 at 4 megahertz. Quite interestingly, I've done that at 4 megahertz to show you that the baud rate is all calculated for you automatically. And what we see on the screen, if I stop it, disconnect, if I disconnect, and I zoom in a bit further for you, you can see it says less than L, it means it's moving in the left direction, and you can see that the LED value is going 1, 1, 1, 1. It's moving, it's cycling through with an ADC value of 490. So if I actually connect it back in, I'm just going to ensure that we've got the bottom number. If I push the button, it goes to the right. The ADC value doesn't change because I didn't change the potentiometer, but the values are now going to the right. So it's going 8, 4, is it 8? Let me just think, 1, 2, 4, 8, 4, 2, 1, 8, 4, 2, 1. And that's the rotation going on inside the program. If I change the potentiometer, obviously the LED goes slower, but I'm rotating it. I can see the rotation value, and things go faster because they are faster, because that's the weight that we put in last time. 1,000 is the maximum, and the minimum is 1. So the program is running exactly as we expected. How do we make that all work? And that's the secret. How do we make this work? Well, if we go back into our source program for one moment, we're just going to change the frequency here to, I don't know, 48, program it out, and without changing, you don't have to go into the details because we have specified that we want to use 9,600 BPS. It will still work. This window will still work. The frequency isn't the determining factor. There it is, 48 megahertz it's running at, isn't the determining factor. You don't have to recalculate it. It does that automatically. So what we're going to do is recreate this from the 101 program if we can. Let me close down 100. Here's the program. If we put it back in there, it won't do anything. So Control A, I'm just going to fold everything up. So we've got everything folded. So the first thing I'm going to do is I'm going to add in my TX in here, which is where I've got my COM port. That's where I've got it, and that's where I'm going to keep it, okay? So just for my documentation, I'm happy now, okay? Now, where shall I add in the constants? Where shall I add it? Where shall I add in the PPS? All I've done there is add in the TX in under 7 here. So let me just show you. I'm going to add in the setup for the serial. Two things we need to do is set up and tell it the baud rate, and then we're going to set up PPS. So I'll put it up here to set up the baud rate, etc. Type __ USART setup, and it will set it up for you. Done. There is no more to be done. It now says 9.600, and it sort of highlights that so you can change it. There we go. One piece done. You can ensure that you send all the data out by having TX blocking. We recommend that, and with no delays, okay? And you can change the delay if your device is slower, then you might need it. I mentioned PPS. Let's put PPS in here. Now I've got PPS open, so just look away whilst I close it because I want to show you how to open it. Function key F4, inside the IDE, PPSTool. There it is, enter. It will open up the PPSTool. Zoom in for you. Bring it into focus. Let me zoom in some more, shall I? Oh, there we go. Even better, look. Select the correct chip. There are many chips. A peripheral output, that's what we're using, peripheral output. Scroll down, TX1. TX1 means transmit USART1. In this particular chip, there are two, I believe. There's two. And you can't see it on the screen, so I will just move that up so that you can see it. TX1. Just move it down. Which port do we want to connect it to? RB7. Add. It has created a subroutine, and that subroutine has got a special code to say connect RB7 to the capability TX1. Copy. It puts that in your clipboard. Back into our IDE, shut that down. Control V in here. If only I'd actually done it correctly. I clearly didn't do that correctly. TX1, add it in PB7. I am not going to zoom in. Copy. Control V, it puts everything in there for you. I'll walk you through this. This essentially means here's the subroutine that's going to get called, and it will set up that capability. This is the startup, which says when this program starts, call init PPS with a particular number. That number just makes sure it's early in the process. That's documented in the help. So it essentially says it's going to call this automatically. That is the serial set up. There is no more to be done. We're done. Now we can add in our program what we like. So down here, let me just think where we're going to put it. Before the do loop, okay, before the do loop, in here, we're going to add in some commands. H serial print a string, H serial print string, hello world, and we won't do that. Demo, what was it called? Oh, I think there's a new constant, isn't there? There's a program, 101, demo 101. It will put that on the screen for us, and it will print demo 101. Why don't we just show you that? Function key F5 to program. Now, if it's worked, we'll see demo 101 on the screen. That's it from the reset from the previous demo 101. Can't see it? I'll just zoom in for you. That's it. Let's go into our program and put some stuff in here now then. Get the value of the ADC port. Let me just think where we're going to put it. We'll take the value of M delay. And what I'm going to do is I'm going to take out that carriage return line feed from that 101, and I'm going to do some formatting here. Oh no, I'll put that back because I want to do it differently. Right, what's the value? Let me put it here. No, I'll put it down there. H serial print my delay. So that will give us on the screen the current delay value. Simple as that. And it will treat bytes, bits, and long numbers, and it will just format them on the screen for you. And after that, I'm going to send it H0 send a 9, and that 9 is a tab. Here we go. Great. Set the LEDs. Right, if it's going to the left, H0 print L, else, H0 print R. So, right. And these are just simple commands. And after that, at the end of the if statement, we'll put another H serial send a 9. There we go. Now, at this point, port C, the LEDs, we can display them on the screen. We can pull that out, the value. So what I'm going to say is H serial print, and I'm going to use a couple of functions here to make it all work. I'm going to take a string that's created. I'll do it the other way around. I'll build it up and from the inside. I'm going to take I want a binary value. So if I type in B, a binary value, I can take a byte and take it into a binary value. So it will take any value between 0 and 255 and turn it into ones and zeros. And I want to take port C. That's where our LEDs are. But I don't want to say all 8 parts. I want to say the left 4 parts of that string, because that's a string. So left, byte to bin, there we go, port C, and it will put that on the screen for us. So what we've got is that whilst we're here, H0 send 9, which is a tab, H0 print a byte value. Now it's a print value of my. Have I printed out my delay? Oh, I've done it there. Okay. Oh, I don't know. Let's put a carriage return in here instead. Print carriage return line feed, and it will just loop around. Program that. No errors. That's great, because we knew the program was working anyway. Zoom in. We'll see what happens. Demo 101. Hey, 338 is the current value of the ADC. It's going to the left. And if you look at the numbers, they are rotating to the left. If I push the button, takes it to the right, and the LEDs move in the opposite direction. If I rotate the pot, it goes faster between 1 and 1000. That is exactly what you expected. And trust me, when I developed these programs a year or so ago, I had to use the serial to get it all sorted. It wasn't that easy, quite clearly. So serial is the absolute wonderful thing for debugging. You can just put as much as you like in within the constraints of the memory and within the constraints of the microcontroller. So what we've seen is we can easily add input and output on this particular program, and we can see what's happening when I push the button. It goes to the left, it goes to the right. It's got all the information that we need, and we have it formatted on the screen. What we can also see in here, in this terminal, is if I press the time button, it actually puts in the time it was done. And if we look at that, when it's 4:04, it should do it twice a second, shouldn't it? If I put that full on for 1000, it should do it approximately every second. Look at that. That's pretty close. Now this isn't a controlled frequency. This is just an internal clock running, and you've got all the other things going on within the 1000 millisecond delay. So you've got all the other code. You'd have to do some tweaking, but it's close, and that's the point. If I change the frequency to another frequency, then it will still do that. So let's go back to the editor, and we're just going to look in the IDE at 10 at let's open up 100, the reference piece of code, and it's got some constants in here which I used. It said like in here, chip string, chip name string, chip megahertz. Those are values, just the constants. If I press F1, which will bring up the help, I've got lots of these things, and I can then say, okay, great. If I want to know the source name of the program that's actually running at the moment, I can go back into my program and see that. So let's just add that into our little program. Demo 101, coach turn line feed, and I've just changed that for source file. So rather than saying 101, it's got source file into the terminal. Zoom in for us so we can see it. Demo 1 as it resets. Oh, there we go. I'll just disconnect so we can see it. 101 reversible LEDs with variable delay to serial terminal. Well, it got it from somewhere. It got it from the GC Basic compiler. Okay, bit of a long one, but it's worth it. So, done. Hope you enjoyed that. So, we've seen serial working. Now we're going to use timer overflow, 8-bit timers, 16-bit timers to flash those LEDs. We're getting deeper into the microcontroller. Using timers, great stuff. Part 8, enjoy.